Okay. Okay. Good morning. I'm Katie Cottingham, and welcome to this news briefing from the 254th National Meeting and Exposition of the American Chemical Society in Washington, D.C. We're joined today by Dr. Yuqiang Bi from Arizona State University and Dr. Shauhrat Chopra from the University of Illinois at Chicago. They're studying the environmental impact of quantum dots in discarded TVs and tablets. Dr. Bi?
Thank you. It's a great pleasure to be here. So my name is Yuqiang Bi. I'm a researcher at Arizona State University. And both of us are part of the network of LC Nano. So it's a project funded by US EPA on life cycles of nanomaterials. So many of you know that over the past decade, nanomaterials has been increasingly incorporated into consumer products. And great uncertainty actually exists in our ability to predict and manage the risks associated with the nanomaterials across their life cycles. So here, Shauhrat and I are looking at a quantum dot. It's a semiconductor nanocrystals that's been used in many electronics. And so, as shown in this picture, we have a quantum dot. Materials has very distinct photo and electroluminescence properties, which you can shine the light to it, and it exhibit very distinct colors, depending on the size of the nanomaterials. So with the smaller size of these nanocrystals, you would have a green light emitted, and at bigger size, slightly bigger, you have red light. So we typically have quantum dot with the chemical component of group 2 or 6 or 3 or 5. So the most common ones are made of cadmium selenide. And emerging quantum dot materials are made with indium phosphide. The reason we focus on these two materials is first, the cadmium is toxic. So it's been regulated by EU, so European Union. And manufacturers are looking for alternatives of making their electronics, especially displays, with a less toxic material, so as indium phosphide. So that's why we're looking at the life cycles implications for both of these nanomaterials. So we can go to the next one. So I will give the opportunity to Shauhrat, who's looking at the life cycles of such materials.
Yeah, thanks, Yuqiang. So as Yuqiang mentioned, we are doing this comparative assessment so that we can make a sustainable design informed decision for manufacturing of emerging technologies. And the emerging technology that we are looking at is quantum dot displays. And the major issue with these is that, if you remember, when the first phone came out, it was $2,000. Now you can buy it for $4. In the future, we're going to get them for free. They'll be just given out in, cereal boxes. And you will have them everywhere. And the issue is, how do you dispose them? And there's a design issue in terms of choosing cadmium selenide over indium phosphide. And you need an in-depth, thorough analysis with the entire life cycle, going all the way from resource extraction to manufacturing of these nanomaterials, then incorporating them into the displays, then looking at multiple product lines that they're incorporated in. So basically going through the entire value chain of the product that this new technology is being embedded in. Because what the ultimate goal here is to have a sustainable design decision based on such that we do not displace the emissions from one part of the life cycle to another. So we don't say that, hey, it's more toxic. So cadmium selenide being more toxic means that let's use just this one particular material property to make the entire regulatory decision regarding an emerging technology. So we require this in-depth study. So for that reason, we do life cycle assessment. It's basically an emissions accounting methodology. So it's like economics, but we are accounting for carbon, we are accounting for various environmental impacts. So one of the things that is very important is the end of life of these products. So we're particularly looking at a product, a tablet from Amazon, which had quantum dots using cadmium selenide. And we're comparing it or using Samsung indium, which uses indium phosphide, quantum dots, using the same technology for incorporating the quantum dots in the displays. And we're basically running experiments to understand the release of quantum dots from the end of life, using a couple of different scenarios. We're looking at whether they put in a landfill, what happens then. So we simulate a landfill environment. And we also are planning to do the incineration scenario, where we would incinerate and see how the fly ash would change with respect to the cadmium and the indium in these electronics. So I'll hand over to Yuqiang to talk more about the experimental side of things.
Okay, so we can go to the next slide. So as Shauhrat mentioned, that this is a truly collaborative work. So he's a LCA practitioner, and I am an experimentalist. So we look at both the manufacturing processes and end-of-life processes. And our goal is to reduce the uncertainties that now, because of the limited information we have from the manufacturers. So I have been looking at the end-of-life scenarios for the quantum dot displays. So we're looking at the option of disposal, which is a very typical way of solid waste disposal way. So for this study, we actually have electronics. Here in the picture is a tablet. It's made from Amazon. It's a Kindle 7-inch tablet, and with a broken glass or LCD display. So with that, we chop them into smaller pieces, as shown in the picture, 1 by 1 inch, and we place that into the batches. So it's basically plastic bottles, and we prepare the simulated leachate to simulate the landfill conditions. And we have a solid to liquid ratio of 1 to 20. So that can simulate the landfill leaching for about 10 years within the experiment of 18 hours. So with that, we measured the concentrations of metals after this experiment, and specifically look at the leaching of cadmium, indium, and selenium, which are the RCRA, so Resource Conservation and Recovery Act, a determinant for toxic metals. And with that experiment, we actually found very little leaching of such heavy metals. So they only account for less than 0.02% of the total metals embedded within the polymers. Actually, we should mention that the quantum dot materials are embedded within the polymer to make it very stable. That's intended by manufacturers, and our results just confirmed they're actually pretty stable within these polymers. And I think from our results, they pose a pretty insignificant hazard for this landfill scenario.
Okay, so are there any questions? Please state your name and affiliation when you're asking your question. Ben, so we have the microphone. I don't think it's on. The microphone? Is it on?
Well, that's better. Ben Valsler from Chemistry World magazine. How do you know that your leachate is a good proxy for real landfill conditions? Have there been other experiments that compare to real landfill in order for you to have a really good certainty that you're seeing a realistic picture?
Okay, so that's a very good question, Ben. We have to use standard methods to compare with the actual landfill conditions. So we use the EPA standard methods. It's called TCLP, TCLP, and that's basically have a number of salts and a pH of 5. That's buffered by acetic acid. So with this chemistry, and this has been very commonly practiced in such simulations. And you may ask, is it relevant? And I will say this is the best method we typically have for such conditions. And EPA will actually use such information to determine that if the metals present in the leachate is above their standard or not. So we can regulate how we can dispose of our electronics.
And do you have a good handle on what the background levels of these metals are anyway? So obviously we wouldn't necessarily see the quantum dots in nature, but there will be background levels of cadmium naturally there. How does this compare to the background?
That's a good question. So what we have for the experimental scheme is we have a 3-tiered method. So first, we have our experiments set up with the only quantum dot film. So supposedly, with that film in the leachant, you have the maximum leaching of metal. So that sets up the upper boundary. We have a background information from the rest of the LCD display components. So we also did similar things with this. And eventually, the third tier is that we have the entire display cut into small pieces and repeat the experiment. So then you can have the entire information. But because the film is embedded within the LCD assembly, we suppose this information gives you the lower boundary of leaching. So we have the 3 tiered results. And our results show that with the upper boundary, you have about 1.3 ppb, so microgram per liter of cadmium in the leachate. The background is less than 0.2, so it's much lower. And the lower boundary is also lower than 1.3. Yeah.
So with this in mind, and with your prediction that we're going to see ubiquitous quantum dots in the future, will there be a threshold at which there are a certain number of tablets or televisions being thrown away, at which point we do say we need to look at this data again because we think it may now be a problem?
Exactly. I mean, that's exactly what we're mandated to do in this project. The idea here is to set up those prospective scenarios of, say, 100% adoption, where all technologies move to quantum dots, or we have a more conservative estimate, and we want to basically use probabilistic scenarios that we would build such that we get a good idea of uncertainty, as well as get a perception of what the implications of our designs at the present stage with respect to the quantum dot types that we choose, the technologies that we choose, the products that we decide to put them in. All of these things have large long-term implications when you start considering the possibility of large-scale adoption. While at an individual tablet or TV scale, the results might seem insignificant, but when you start accumulating them, and you start seeing the cumulative effect of having so many of these in unlined landfills, or being incinerated somewhere, or being shipped somewhere else, we're basically displacing our responsibility, or in a way, we're basically displacing our emissions to another part of the world, which again, in a global context, doesn't really make sense. So having said that, life cycle assessment does allow us to do mostly retrospective assessment of existing technologies, because it requires a lot of information to do one of these models. So in our case, what we're trying to do is develop a framework where we could do an iterative life cycle assessment, where we start with basic information, minimal information with high uncertainty, and continue to narrow it with extended collaborations with experimentalists, because ultimately the information that Yuqiang provides is only useful for making a decision when it's put into the context of the real world scenarios. And that's what we're trying to do here with looking at quantum dot technology, because it's most of the times the nano technology that we have seen out there has been a single element nano particle that has been embedded in a product. That's mostly the case. But at this time, what we're seeing is these complex heavy metals being combined, and they have their own interactions in the environment, and they leach different rates at different rates. So there are a bunch of questions that are force us to look at this prospective analysis of emerging technologies.
Thank you.
Okay, other questions? Bela.
Bela Busrig, ACS News Service. What's the actual lifetime of these displays? Like what are we talking about when you start producing the displays and then that eventually need to be disposed of? And why not start working very effectively on recycling everything? Indium is not exactly the easiest thing to get. Cadmium is not so bad in that respect, but still, recycling might be the effective way of doing things.
Should I take that?
I would just first mention about that's truly the case. So actually, in order to study our study, we actually bought a broken TV. So that's actually a way of recycling the products. So we bought our products directly from eBay sellers. Mm-hmm. And we actually had many stories of purchasing the right product. And Shauhrat actually talk about the other ways of the end of life.
Yeah, I think that's a great point. You mentioned this issue of how many and what is the time period, and that's exactly what we get into in life cycle assessment. The question is how each of the point is that each of these devices have a very different lifetime and the rate at which you dispose them. So if you have a smartphone, you would dispose them very frequently in comparison to a grid-connected television. Because you just have it mobile, you tend to break it, they go obsolete. There's technology change happening at a much faster rate at the smartphone scale. So your point being, we can recycle these technologies, but the point here is that recycling might actually not be the most environmentally efficient way of dealing with the the end of life issue, right? Think about it, because you have indium and cadmium in these quantum dots, but we have to remember that these are nanoparticles, and there's very little amount of them in the display. And the background issue that we already have indium titanium oxide or indium tin oxide, the ITO films in displays already, which is part of the entire display itself. So there is background effects too. What we're trying to do here is look at what are the QD specific impacts. Like in terms of there's very different life cycle emissions of a bulk material. So bulk cadmium selenide would be very different from nano cadmium selenide and how it interacts in the environment. So getting at the point that whether recycling is the answer, probably not for all devices. So maybe for smartphones with a higher rate of change, but with televisions, I don't have a certain answer. That's what we're doing here, but it's not as easy as just saying that let's recycle all.
Okay.
Thank you.
Other questions? Do we have anything online? Okay. Doug, do you have a question? Or Okay. Well, if that's all, then thank you very much for joining us today. The archived version of this session will be soon posted at bit.ly/ACSLive_DC. Please join us for our next press conference at 9:30 today on a muscle-inspired glue that could make fetal surgery safer. Thank you.